Hi guys, so today we're going to start our nuclear chemistry notes. We're not going to finish them today, and that's fine. I am just going to kind of go over what nuclear chemistry is and how it works a little bit, and how we discovered it. So nuclear radiation is basically an atom breaking apart. And so, or two atoms coming together to make a larger atom. So it's either two atoms breaking apart or, one atom breaking into two atoms, or two atoms coming together to make a larger atom. And in the process, the energy that is emitted from the binding of the atoms or the breaking apart of the atoms is what becomes the radiation. And so an atom, you guys, we went over this last semester, but hopefully this first slide is just kind of a refresher. So an atom was initially thought to be the smallest unit of an element. It was supposed to be the unbreakable part of an element. We know now that that's not true, but that was what it was supposed to be. So an isotope an isotope is elements that contain equal number of protons, but different numbers of neutrons in their nucleus. So just like you can have carbon-12 and carbon-14, what the difference is the amount of neutrons. And so those are two isotopes of carbon. So a long time ago, X-rays, radiation was a lot more everywhere than it is now. Some people like to think that it's like, oh, it's so everywhere and it's harming us. Actually, we have a good handle on it to a large degree now. So radiation is emitted from your microwave and your cell phone and all kinds of different things in your life, but it's emitted at levels that your body is not going to cause you problems to be exposed to. A long time ago, when we didn't really know what radiation was, and before we figured out what was exactly happening with elements, we used radiation for all kinds of things. You used to be able to go to the local shoe store and get your foot sized by an X-ray to get your perfect fit. It was a marketing thing that was at all kinds of different shoe stores. It wasn't just like one. You could, as a child then at the time, go in and like sit on these and play on these, and that was a whole lot of radiation exposure. Kids would go in and be like, oh, look, I x-rayed my foot. And then they'd be like, oh, look, I x-rayed my hand. And now look, I x-rayed my butt. It's like the coolest thing. And it was so popular. And it was at every like drugstore on the corner. You could go in and get an x-ray. And so people were and this wasn't the only thing either. People were being wildly overexposed at this time, and cancer rates kind of went through the roof not too many years later. And this is part of the problem. But we were messing with something we didn't really know what it was. And so because of that, we had all kinds of problems. And that's understandable with anything, that especially when we have no research on it and we're just messing around. Like, you should never do that. You should have research on something before you put it out for public use. So one of the first people that started doing tests with things and figuring out that we had a weird phenomenon here was Henry Becquerel. And he started doing all kinds of things with uranium, and one of the things that he did was he had a piece of paper that was like film paper that he put underneath some other papers, and he put the uranium sitting on it, and when that happened, it made these marks on the paper. So he noticed that this photosensitive paper was turning colors in presence of the uranium. And he started doing some tests in it, but he noted it as a property of uranium. He didn't realize that this was a property of many elements, and that many elements were radioactive. He just knew that, and they didn't even know what radioactivity was yet. actually, and radioactivity was not even a term that they used at this point. So they had no idea, no real clue what was going on at this time. And then along came Marie Curie, and she was from Poland. This was during a time in Poland when women were not supposed to be taught, and they weren't supposed to get an education. She came from her parents were both teachers, and so she was taught at home, and so was the rest of her siblings. She actually had after she got done with her homeschooling, or her schooling by her mother, mostly by her mother, who educated a whole bunch of girls and children in the area. She went and got a job and worked to help put her older sister through school before she left home. And Poland was in the process of, other countries were trying to wipe it off the map. They were trying to remove Poland. And she came to Paris and she got a degree. She was actually one of the first women to get a degree. And during this time is when she met her husband, Pierre, and she very much wanted to follow her science, and he was very much into science. And she kind of ignored him for a long time, and finally she decided that she was in love with him, and she did love him, and then they got married. And during this time she's doing all this research, and he's working as a professor at a local college. And she's, she has their daughter, and she continues to do this research. And she had initially started her research just kind of noticing something about uranium. She noticed that there was, like, if you put uranium between two electrical currents and then tried to turn the thing on, that it would still work if uranium was between the two electrical cords. And then she was like, oh, well, that's really neat. What if I go see if other elements have this possibility? And so she started doing tests to all kinds of other elements and other materials, and she noticed that other materials had it too. And then she tried to isolate the thing causing the electricity to go through the air current, or to have a current through the air. And she discovered other elements that nobody knew existed. And she started isolating those so that they could be properly tested and cataloged. And the first one that she named, she called polonium, after her home, Poland. And the other one she called radium, because it emitted radio waves, or radioactivity. And so they were both radioactive, and she actually coined the term radioactivity. Her Nobel Prize, she got two in her lifetime. Her first one was actually recommended to her husband, and her husband absolutely was like, nope, I am not accepting this, without my wife's name on it, and I can't do that. And so because of her husband, even though he had very little to do with her work, they tried to issue it to him, and he refused, and so they issued it to both of them. So she got a Nobel Peace Prize awarded to her and her husband both for her work that she mostly did. He helped devise the instruments that she used to measure the radioactivity, but he didn't really do a whole lot of the work. So it was her work, it was all her time and her effort that she was putting into this. And she worked in an old shed most of the time. But she discovered two elements. She coined the term radioactivity, and in her lifetime, she got two Nobel Peace Prizes, both in different fields of science, actually. So she was a brilliant woman who gave us the information we needed to realize that the atom was not an unbreakable element. So in this time, I shouldn't say unbreakable element, the atom isn't unbreakable. So initially the thought was that atoms were the tiniest thing that was unbreakable. And that wasn't the case. So Ernest Rutherford came along and he's like, well, with what her science says, I'm going to go along and do these other experiments. And that kind of led us down the road that atoms have a lot of space in them. So we actually talked about this once before last semester, where we talked about the gold foil experiment and how if you throw something at a solid surface, it's not going to go straight through, it'll hit it and bounce back. Well, most of the atoms that he was shooting at this gold foil were actually going through. And that's because they were fitting through the spaces between the nucleus and the electrons. So I told you guys last semester the atom is about the, like, if you were to go to a football stadium and stand in the middle and you were to hold a golf ball, while you would be holding the nucleus, the electrons would be the very top of the outer rung of the football stadium. And that's how much space is in an atom. And this is part of how we found this out. Marie Curie was the one who helped us figure out that and do experiments to test whether or not the atom was a solid object that couldn't be broken, or whether or not the atom could be broken apart in smaller pieces. And so she's the one who helped us discover that the protons, neutrons, and electrons were there. And a lot of this information about science rests on her information. It came from her information. So she is just a brilliant woman that helped us develop all this information about radioactivity as well as atoms. So alpha decay is the least dangerous. It's the largest, and it's not really that harmful. Alpha decay is when an atom breaks apart into two, but the one part is so big it's almost the size of a helium atom. And because the piece that breaks off is so big, it can actually just bounce off your skin. So it's not really all that harmful. It's not really harmful at all, I should say. So this ion consists of 2 protons, 2 neutrons, and has a +2 charge. And you can see down here a chemical reaction, and you can see that we start off with uranium, and it goes through a reaction, and then you can see, like, we had 238, now we have 234. Well, where did the other 4 go? It's over here. Same thing here. We used to have 92, now we have 90. Where are the other 2? It's over here. And so this is an alpha particle. And so we really need to know what an alpha particle is, and that this is an alpha particle. So make sure we have make sure you have that written down somewhere. It's important. And you're going to have to be able to identify it later. Beta emission involves the transportation of a neutron. So you take a neutron and it changes into a proton and an electron. So one neutron is like a proton and an electron. The electron is then ejected from the nucleus. So it's shot out. In the process, the atomic number increases by 1 while the atomic weight stays the same. So you can see we have the atomic weight here, and this is our proton number. Well, our atomic weight stays the same because we eject the neutrons. The neutron comes out. It breaks apart into 2 pieces. The proton, which has the same amount of weight, right, as a neutron, and then the electron, which has basically no weight, and it gets ejected. So this is what a beta particle looks like, and it's not extremely dangerous. It can hurt you a little bit, but it's not terribly bad. So this is like the next step, and you can see that this is something smaller than the alpha decay. Now here we have gamma radiation. So gamma radiation, there is no change in atomic size or atomic number or anything. It's literally the release of energy. And this is the most dangerous. This is so tiny that it actually moves between and through the parts of your atoms. And that's why it's so harmful. This is the stuff that's like, it can be deadly. So this is the terrible type of radiation. And this is what you don't really want to be in the presence of. So gamma radiation is always depicted with this, and generally you have a little 0 and a little 0, but that's what it looks like when it's written out in an equation. You don't have any missing protons, or your mass number doesn't change at all. And so it would be the same element again, and it would be releasing energy. So to pick it out, if I were to show you examples, you would depict it by this little, it looks like a funny Y to me. So, but that's gamma radiation, and that is the most dangerous. And we'll go into tomorrow, and like tomorrow we'll look at how you tell the differences in chemical reactions and how you would write them. Okay, so go ahead, get these notes down, make sure you have them, and hold on to them. We're not done with our notes yet. We'll turn them all in at the end when we're done with them. Okay. Let me know if you guys have any questions.